Hello, welcome to the second part of the presentation on higher order differential coefficients. In this presentation, we're going to cover the transcendental, which are the exponential function, natural base, the trigonometric functions, and then the outcomes of this presentation are as follows. By the end of this presentation, you should be able to compute the nth order differential coefficient for the function y is equal to e to the power ax, the function y is sine ax, and y equals cosine ax without using successive differentiation. I repeat that successive differentiation I refer to, let's say you want to obtain a derivative of order 5. You have to do the computation literally 5 times, starting by the first order derivative, second order derivative. So the essence of this presentation is try to relook at what we have done, we've been doing so far, and try to find a way of computing nth order derivatives without necessarily going through first order, second order, third order, and so on, which I call successive differentiation. So let's start with this function, the exponential function e to the power of ax. We are all familiar with the fact that if we're given this function as y is equals to e to the power of ax, we know that in this different function, whenever we differentiate this function, the root function itself, where we start from, normally bounces back, multiplied of course by the derivative of the argument. So in this case here, the first order derivative will simply be a e to the power of ax, and then going to the second order, this will be equals to a brackets a e to the power of ax. So what I'm talking about here, like at this stage now, take this a as a constant, then differentiate that, which gives me that, which at the end of the day, this gives us a squared e to the power of ax. In this case, if I use that notation and say y second order differential coefficient, we can see already what we can see, something happening here. If we use that notation here, is simply here y first order differential coefficient, and here y is power 1. So if we go to the third differential coefficient, we see that we're going to have a squared here, this number, multiplied by the derivative of this function, which will be a e to the power of ax, and then that simplifying, you'll see that it's going to give us a to the power 3 e to the power ax. Now I think this is very easy to now take to the general case, because this you can see here, first derivative or first differential coefficient, we have got a power 1, second one power 2, power 3 for third one. So in which case we can simply now generalize it. The nth order differential coefficient will simply be a to the power n e to the power ax. Like you can see here n is written with brackets to indicate that this is a differential coefficient, but here n is simply a power, meaning repeated factors, and I would say repeated factors of a, repeated n times. That's what it is. So in that case, it takes us to the conclusion that they are given a function like this, the nth order differential coefficient will always be of this form. And then we don't necessarily need to actually, if this was 5, to differentiate 5 times, we just have to know that, like as we know our power rule or another rule for differentiation. Now moving forward, we're going to look at the trigonometric functions, which are y equals to sine ax and y equals to cosine ax. Now, in order to understand what we're going to do there, we need to recall something which we did at school. Like if we're given a graph like this, we need to talk about what we used to call horizontal shift of a graph. And if we're given a function like this, y equal to f of x, it doesn't matter what expression this f of x is. It could be a parabola, it could be a line, it could be a trigonometric function per se. If I now create another function, which I can call, say here, f of x minus h. Normally, in my introducing these things to my students in the first time, I normally want them to read this minus as shift by. Just interpret it as shift by. In this case, he's saying the function f shifted by h. But shifting by h, our natural direction of movement in this case is to the right. In this case, this function would be shifted to the right by h, which you are illustrating here, that if you've got a function like this and we rewrite that function with this kind of an argument, this function will be moved horizontally in a rigid fashion and be plotted here at it, and in other words, the point of intersection here, there it was x0, there it will be simple x0 plus h, meaning is shifted horizontal to the right. And then on the other hand, if we instead of shift here minus here, we've got a plus sign, we should understand that this plus sign we can sort of unpack it and rewrite it as a minus h. Again, this minus sign, I can still read it as shift by. In this case, says shift by minus h, meaning the original curve, which is here, is going to be shifted to the left by h. So in other words, if this was x0, and then this function would cut here at x0 minus h. In other words, it's actually being shifted to the left. That is very important to understand what we're going to do now. Now, let's consider the function y is equal to sine x. And this is its standard curve, in this case from minus pi to 2 pi. That's what we'll do. So now, we can't talk of sine without talking about cosine, because actually cosine is nothing other than sine of the complementary angle. Now, cosine is sine function of the complementary angle. In this case now, we are going to look at cosine of ax. So the graph of cosine then comes in this way. We all know that at 0, here where x is equal to 0, when the argument is 0, that will be 1. That's how it looks like. And then at half pi, we know that it is 0. So what is important here in terms of horizontal shift, it is important to see that the two functions have got exactly the same shape, and actually we can start from sine and end up in cosine by just shifting the sine function to the we saw before. That is the shifting which would result from something like f of x plus h. In this case, let's say this f was sine, then it would need to be shifted to the right, to the left by h. In this case, what we know, this is the identity we know from long back, that cosine of x is equals to sine of x plus 90. I'm trying to just use what you start with, but in this case here, we're going to work it in radians, so then it is still the same thing, that cos of x in radians is same as sine of x plus half pi, which is an equivalent angle to 90 degrees. So I'm going to rule out this thing of 90 degrees because we're not using degrees here. Then what we're illustrating there simply is that this is the sine curve, the blue one. If we shift it to the right, to the left, you can see that it coincides with the sine. In other words, what we're confirming, we're confirming exact the same thing, that cosine of x is equals to sine x plus half pi, which is actually, we've just seen that this says x minus half pi. So we're shifting this to the left. So then coming to differentiation, if now we're given the function y is equal to sine ax, we know definitely that the first order derivative or the first differential coefficient is going to be a cosine of ax. And as we're taking the immediate derivative of sine as cos, and then multiplying by the derivative argument, which is a. And then this, we can now change it to and write it as sine, with of course with the coefficient a here, as sine ax shifted to the left by half pi. That will be the first derivative. Now coming to the second order derivative, this will be a constant. Now, if you can see what I did there, differential is sine, but I've changed cosine to sine. Then I can still continue differentiating sine here. Okay, differentiating here, we must note that the argument is ax plus half pi. but half pi is a constant. So when you differentiate the argument, the derivative of the argument is going to be a again. So differentiating here, we're going to have a, this a we have here, in brackets, we're going to have a cosine, in brackets a x plus half pi. So this is derivative of that side. But again, I can remove the square brackets there and have a squared cos ax plus half pi. Now, if I follow what I did here, again, shift and look at this cosine as a sign which is shifted by half pi, then I will have to write here a power 2 sine in square brackets ax plus half pi shifted again by to the right by half pi. That's what would get there. Then if we continue, we look at this now, we're going to have here a squared sine, and then add these two here, we're going to have ax plus 2 times pi over 2, which in this case suggests that if you check what's happening here, already we're coming up with a pattern here. First it was 1, and this side it was the order of derivative. Now here is 2, and this side is order of derivative, and then we got a power 2 there. So taking this to order n, I think it's very clear that this will take us to a to the power n, because we have differentiated n times, and this a would have come out of as a derivative argument n times, so it's a to the power n, and then this will be sine brackets ax plus n pi all over 2. So this will be the nth order derivative of the trigonometric function sine ax. So concluding, this takes us to that if we're given a function sine ax, then the nth order derivative will always look like something like this. So this actually takes us to a situation that if we're given, let's say, function y is equal to sine 2x, and I need here the 10th order derivative. So I'll simply quickly take 2 to the power 10, and then have here sine 2x plus 10 times pi over 2, and then simplify that as simply 2 to the power 10 multiplied by sine 2x plus 5 pi. That will be the derivative. I hope that is understood. Then moving forward now, we need to look at the cosine function. But the discussion, the arguments are very, very similar. But in this case, let's look at the following situation. Now, notice that I've added another curve here, which is y is equal to minus sine, which simple result, we get this by simply multiplying the original sign here. Let's say we multiply that sign there by minus 1. It will come this side. Then the curve comes as the dotted curve here. So now what you must actually notice there is that now if I have got cosine here, the red curve, and actually shift it horizontally to the left, it coincides with the dotted curve. So if we do the same kind of discussion we've just had about sine ax, you will notice that the nth order differential coefficient will be given by y. Nth order differential coefficient is equal to the a to the power n cosine ax plus n pi, which is exactly the same kind of pattern we saw with the cosine. So here I don't think there's any need for a lot of discussion. I think you should be comfortable with this from the experience we had with the sine function. Then, as you can see, we've discussed the three functions, which are what I've called here transcendental functions, which are y equals to e to the power ax, and y is equal to sine ax, and y is equal to cosine ax. And now we can actually obtain their nth order differential coefficients directly without using successive differentiation. So in that case, you can now take the following exercise and practice and leave your answers in simplest form. As you can see here, at the end here, I've got exercises which actually combine what we've seen before, like the polynomial function, the constants, and so on. All what you need to remember is that if you differentiate a polynomial function beyond its degree, like for example, let's say we've got y is equal to x squared. If you differentiate this to order 3, for example, we should know that this is always going to get to 0. Because this already at order 2, we notice that this would give us 2 factorial, which is already constant. So beyond that is going to be 0. So that you must use in some of these exercises where you find these trigonometric function in combination with polynomials. That is very important. Otherwise, at this point, I would like to say thank you for listening. My name is Charles Swelsfani.